In Packet Tracer 13.2.7, you're given a pre-built scenario. Here's a LAN, here's a LAN, here's another one, and here's another one. 2 of them are IP6 LANs, and 2 of them are IP version 4. And then we've got one WAN here in the middle consisting of these 3 routers that are interconnecting everything. And when we look at our starting point, we're at 0% completion. So there's some things wrong in this scenario. We're going to use ping and traceroute using ICMP messages to test the network connectivity. And this is something that would be applicable in real life. Some networks do not allow ICMP messages for security reasons because something as useful as ICMP and ping and traceroute, unfortunately, can also be used in a malicious way to try to deny service to a network by using ICMP messages. So some networks don't allow ICMP to be used. It's good to know how to use these tools in the event that you can, because they're very, very powerful. So the first thing, they give us a pre-filled in table, and part of it we have to fill in ourselves. We start by looking at, there are connectivity issues in this activity. So we're not only going to be gathering and documenting our network, but we're also going to locate the problems and implement acceptable solutions to restore connectivity. We've got the usual passwords, exec is Cisco, privileged exec is class. So the first thing it wants us to do is go to PC1, which is on the IP, one of the IP version 4 LANs. Open up the command prompt, type ipconfig/all. It tells us up towards the top we don't have an IP6 address configured, but we do have an IP4 address on PC1, which is 10.10.1.98. which you can just highlight, right-click, copy, and then go to the table in your document and just paste it. I've already done that. So it's 10.10.1.98 on PC1 is the IP version 4 address. And then our mask is 255.255.255.224, which is going to go in this box right here. And the final bit to fill in on that line for PC1, what is its default gateway? Well, its default gateway has to be in the same subnet, which it is. It's just one IP address apart, which is 10.10.1.97. That takes care of part 1, step 1, A and B. The next thing it wants us to do is do the same thing with the other IP version for PC, PC3, ipconfig/all. And then we go to look at this, which is 10.10.1.18, which is IPv4 host address. The mask is 255.255.255.240, which is a different mask than the other LAN is using. That is actually 28 bits of subnet mask, so that's a prefix length of /28. /28 is equivalent to that .240. And over on the other one, the .224 in that last octet, the other one was a /27. So you just get the IP address, the mask, and again, the default gateway, which is in the same subnet, in this case, .17, and you just populate that information under PC3 in the address table. In E, it says use the ping command to test connectivity between PC1 and PC3. So from PC1's perspective, it's wanting to ping 10.10.1.17, 18 rather. PC3 is 10.10.118, so PC1 is going to send an echo request. There's different codes of ICMP messages, but it's not timing out. There's more information than that. It is actually unreachable. And then if we ping the other way, we should see something similar happen, because normally you really only need to ping one way to determine that there's a problem. So 10.10.1.98 is the IP address for PC1. We have the same indications on either side. So there is a problem here on the network, but we don't have enough information to fix a problem. First, you have to isolate the cause. So our next tool that we use in the ICMP toolbox to get a little bit more information to hone down where the problem is we're going to pull out the traceroute command, which is sort of more of a scalpel in comparison to ping. It's going to use the TTL feature, the field in the IPv4 packet, to give us some more information. So in step 2A, it asks us from PC1, enter the necessary command to trace the route to PC3. The command TRACERT, and Windows will not let you abbreviate. You can't just shorten it. And then we're going to use the same address as before, which is PC3's 10.10.1.18. So the way that traceroute works is the TTL field in the IPv4 packet, remember that's the one that decrements each time it goes through a router to keep internet packets from flying around the internet forever in limbo. It makes a packet timeout after that TTL field goes down to 0. And then what happens is the router at the TTL 0 point sends back a message called a time exceeded message back to the source. ICMP cleverly uses this field in the IP4 packet, and when you do a trace route, it'll send one to the next adjacent hop in that path with the TTL set to 1. It'll get that time exceeded message back. It'll identify who that was, and it will tell you, and it will also tell you the round trip time. And it'll go all the way down as far as it can get through the path hop by hop to that destination, each time incrementing that TTL field, like to 2 and then 3 and then 4, to get those time exceeded messages back and to successfully tell you what is the path that this is taking. So if we go back to the results here, and you can just Control C to get out of that. And it got to 10.10.1.97, and this is the round trip time. It's not getting any further. It's just, so you can just copy this address and copy and paste that into the step 2A. 10.10.1.97 was the last successful IPv4 address that was reached. The packet did not get very far. So the next thing it wants you to do is do the same thing at the other end from PC3's perspective. So we can just up arrow and replace the word ping with TRACERT. By the way, on a Cisco router, it would actually be traceroute all the way spelled out. Okay, so on this end, we are seeing that it's coming back over and over. It's stuck at this 10.10.1.17. In order to answer the question, step 2C, the last successful IPv4 address that was reached was 10.10.1.17. Now we're going to start looking at the router. What we know for sure is if we look at the table of our default gateways, what's the default gateway address for PC1? 10.10.1.97. And what's the IP of the default gateway for PC3? 10.10.1.17. So it did get a response from both of those. So we're starting to isolate the problem. We're making progress because that traceroute indication tells us that everything is good from the NIC on PC1, the network interface card, all the way through the switch to this interface on router R1, which is the 10.10.1.97 address. From PC3's perspective, the fact that it can successfully get as far as the 10.10.1.17 interface on R3 clears this path as being good from the NIC on PC3 all the way to the router interface on R3. We know that means that the problem must be somewhere between this point and this point. And by the way, even when you have all the green light indicators indicating that the links are up and operational on the network, that doesn't mean that the routing is working correctly. That's just telling you that links are established at the physical and the data link layer, but it's not necessarily going to mean everything is correct at the network layer that we're working at right now. The next step in this isolation process, look at R1, step 2F. It says enter the command show IP interface brief, list the interfaces and their status. There are 2 IP version 4 addresses on the router. One of them should have been recorded in step 2A, which it was. The other one here is the serial interface, which is 10.10.1.6. Wants us to record that one in step F right here, 10.10.1.6. The next thing it wants us to do while we're here is to do the show IP route command. On step G, it says list the networks to which the router is connected. R1 is connected to 2 networks through the serial 001 interface. Well, you remember, whenever you address on an interface that is on a router, it's going to create 2 routes. The connected route, which is the network address, .4 is the network, /30 is the network mask, and then it's also going to create the corresponding local route, which is the host address corresponding to that interface. That's the actual IP that the administrator configured, the host address. That's why it's a /32. 10.10.1.6 is the host address of that interface. Okay, so you should fill in that information then in item G. 10.10.1.4/30 is the network. 10.10.1.6/32 is the host address. What I want to do is to draw your attention to the information here. These 2 point-to-point serial links are using a /30, which is very common for point-to-point links in a real-world situation in IP4, just so you don't waste host addresses. So let's put our subnetting hats on right now. A /30 subnet prefix link, that means that we've got 30 bits of network and 2 bits of host bits, right? 32-bit address. So 2 host bits means to calculate the number of usable host addresses, that is, our formula is 2 to the power the number of host bits. So in this case, 2 host bits, 2 to the second power is 4. A /30 is going to have 4 total maximum addresses, and then you subtract 2 to get the number of usable host addresses, because you have to account for the network and the broadcast address. A point-to-point link only needs 2 addresses, 1 for each end. So the /30 is the best choice for that. But what you want to start thinking about is, when you look at a network number, think about what are the usable hosts in that subnet. So this is network 4 in this case. That number is reserved for the network itself. The next 2 consecutive numbers after that are going to be your usable host addresses, .5 and .6. So that means one of these would be .5 and one would be .6. Then there would be .7, which would be reserved for broadcast address, which is for all nodes on a subnet. With .8, it works the same way. 8 is the network, 9 and 10 would be the usable hosts, and 11 would be the broadcast address. And if you ever want to play around with this, you can go online and look for subnet calculators. You should know how to subnet. It's okay to use a subnet calculator to check yourself with the learning process. This is www.subnet-calculator.com. And I'm just going to draw your attention to one of those networks we were just looking at, like 10.10.1.4. If we plug that into the subnet calculator, 10.10.1.4, because 10 is normally a class A type of address. So the default mask would be 8, but in our case, we had 30 bits of mask, right? So you go all the way down to 30. And a subnet calculator is really helpful because you can look at it and you can see network. This is what my subnet mask would be if I had 30 bits of mask bits. How many hosts I can use per subnet that are usable? 2, and they would be .5 and .6. My subnet ID is the .4, that's reserved for that, and my broadcast address would be .7. And you could do the same thing with the other /30 that we saw there. I just want to draw your attention to this as something that you might find useful. Now over on router R3, the show IP interface brief after we log in using the password Cisco. So we had already recorded the 10.10.1.17, which is the default gateway for the other PC. The other address that you want to record in step H under 2 is 10.10.1.10. And then the other two pieces of information at once are from the show IP route. What are the two networks that are connected to serial 001? So we've got the /30, which is the subnet ID, and then we've got the .10/32, which is the interface IP address itself, which is part of that /30. It's one of the members of that /30, which remember, that's going to be .8 through .11. Now router R2 on J, it just wants us to do the show IP interface brief. Record your addresses. One of the serial interfaces is addressed with 10.10.1.2, and one of them is addressed with 10.10.1.9. Apply to step J. We have enough information here to kind of see what's going on, right? On R3, we have .10 in that last octet. That looks okay. That's part of the .8 network. We would expect to see the .9 over here on this side. And there it is. For the .4 network, remember our possible host addresses for that link are going to be .5 and .6. They have to be on the same network. R1 has .6, so that looks okay. On the other end of that link, that has got to be a .5, it's a .2. That's not going to work, right? Because the .2 host address is part of the 10.10.1.0 network, which is the /30, which would encompass 0, 1, 2, 3. What we have here is we have a link which is currently up, but it's not going to be able to route because these two ends are not in the same network. On R2, the serial interface is in the wrong network. So if we go back and look at R2 again, and when we do a show IP route, you see right there, that's not the 10.10.1.4 network. It's the 10.10.1.0 network. So let's fix that. We need to configure it with the right host address. If we go into enable mode and class is the enable password and go into configuration terminal, serial 0/0/0, the command would be IP address, or IP add for short, 10.10.1.5, which will put it in the correct network. It'll put it in that 10.10.1.4 network. And our mask for a /30, you can't put /30, you've got to put 255.255.255. We've got 6 bits of network in the 4th octet, which you're adding everything together except the 2 least significant bits. So that gives you a .252. If we go back and look at the show IP route, we want to see that they're both now in that same network, 10.10.1.4, for that link to function at layer 3. The solution to correct this problem, we have configured the correct IP address on serial 0/0/0. So now let's go back to PC1 and see if we can ping PC3. Yes, we can. Now if we do that traceroute, that's looking a lot better. So the nice thing about Traceroute is too that you can actually see what path that your packets are taking through a network. And if there's thousands of routers in that network, if they do allow ICMP messages to get through, it's like watching a car drive. You know, you can actually see what paths it's taking from end to end. So that's looking much better. And then over on the PC3 side, we can now ping successfully, and our traceroute is looking exactly how it should look. This means that we've fixed that problem and we can go on to part 2. Just fill in yes. And if you didn't get a yes, just go back and troubleshoot. And then when you look at your progress with your packet tracer, you should see a completion point 50% now. So the next part wants us to do a similar exercise, but this time using the IP version 6 protocol, which is going to put us with PC4 and PC2. First thing it wants us to do is click on PC2, open the command prompt, and type ipconfig, because whether it's IP4 or IP6 on a PC, it's still going to be ipconfig/all. It wants you to record the IP6 address, which is right here. This is the network portion. So when we're learning about IP6, remember we talked about subnetting and how, like, if it's using Slack, for example, the router advertisement will provide it with this routing prefix. This is the first 48 bits of the IP6 address. So that is the routing prefix for this network. And then when you're subnetting in IP6, this is the 16-bit subnet ID part of the address, which makes IP6 subnetting so much easier than IP4. So in this case, this is our subnet, which is subnet 1. And then they've used a double colon to collapse all the intermediary zeros. And the host part is this interface ID, that IID part. This is the full IP version 6 address for this host. And this is a GUA type address, global unicast address. You can tell, not a link local address. Otherwise, it would begin with the FE80. So this is the part that you would copy and plug in back up in your addressing table for PC2. Now, this doesn't tell you what the prefix length is. You can usually assume it's a /64 in most cases. That's how most networks subnet IP6. But another clue is you can look here at the diagram, and it tells you that is a /64 network. And you would also know if you looked on the routers themselves. They'll have that information in the routing table. You fill that in with the /64 here. And then you want the default gateway, which in this case, it's using a global unicast address for its host address, but it's using a link local address. And this is its default gateway address, FE80::1. So that would go right here. Then for step 1C, it just wants us to do the same thing over on PC3, or PC4 rather. As you can see, the routing prefix is the same because this is like one company and this is going to be their global routing prefix for all of their subnets. But then the subnet itself, this is subnet 4 and host number 2 on subnet 4. So this is the full IP6 address for PC4, and it has a /64 as it shows us here on the map. And then the default gateway is, again, using the link local address. Remember, those are the ones that are not globally routable. They don't go beyond the local subnet. So the default gateway is using a link local address, FE80::2. So put that in the table then. So the next thing it wants us to do is test connectivity between PC2 and PC4. So I'm just going to copy and paste that in from my table. I'm just going to get rid of that /64. Now, you would expect the first ping not to go because it's got to do a neighbor discovery if it doesn't have that cached in its local cache, but it should, the second or third, the subsequent ones should be successful. This time we're not getting the host unreachable, we're getting a request timeout. Expect that we will see something similar over on the PC2 side. Same symptoms. We clearly do not have a working end-to-end network connectivity in our IP6 configuration either. Again, we're just going to Control-C. That brings us to step 2A. From PC2, let's do a trace. So this is getting the response back from the first 3 hops in the network. Each hop is going to be a layer 3 device like a router. This means that the problem is going to be closer to PC4. That tells us that there's pretty good path for most of the path between PC2 and PC4. The problem is somewhere towards the distant end. Once you start seeing the timeouts, that just means go ahead and Control-C, or if you're on a router, Control-Shift-6. And let's go over to do what the document asks, which is, what is the last successful address? That would be this one. So that's the one that goes into 2A, 2001 DB81:3::2. So over here on PC4, let's see what happens. This is interesting. So on the PC4 end of the network, the first hop would be the default gateway for PC4, right? PC4 can't even get to its default gateway. So that default gateway is like the doorway out that PC4 needs to go out to the rest of the world. If it can't even find the doorway, it's not going to get out of the local network. as you can see how Traceroute is very helpful in isolating issues. Do you notice how PC2 first hop is showing as this address? This is its default gateway, right? Because that's always going to be the first hop. But interestingly, the default gateway address we have completed in our document when we were documenting this is FE80::1, that link local address. This is what I mean about in IP6. We typically will have two IP6 addresses on a single interface as a norm versus IP4 only one, because the link local address is not going to show up on a trace route because it's not routable. It's a local subnet only. So this is the IP6 GUA equivalent. This is the routable address of that interface, which if you go and hover over R1, it's that first address in the IP6 column, about the 5th column over. Because these are routers, these have to be routable addresses. This is the address you're going to get back from the traceroute. The next thing it wants us to do is to go back to see what our last successful IP address was. There was none. It didn't get to its default gateway, so it did not get to anything. So you would just put like no IP address or none reached. Let's then go to R3. R3's interface right here is the default gateway for PC4. So if we hover over that, we're only going to see the GUA address in that 5th column there, which is DB8141. So we want to find out what's going on with R3. Why isn't it able to fulfill its duties as a default gateway for this PC? We go to step F. Enter the command show IP interface brief for IP6. You say it show IPv6 interface brief. And that will kindly show you both the link local address and the GUA on the interface. What's our discrepancy here? There are two IP6 addresses for the default gateway interface, and one of them should match the default gateway address that we recorded in step 1D, which was what? FE80::2. There's our problem, right? So our traceroute showed us where the problem was. It narrowed it down to router R3, the default gateway. And then our next tool that we used was to log in, do a show IP6 interface brief, and to compare the interface addresses. We do see that there is a discrepancy because the default gateway that the PC is trying to use would be ::2. So for our problem description then, if we go down back to that step, we're seeing that we do have a discrepancy. And the error is that PC4 is configured with the wrong default gateway. So that's pretty easy to fix. All we have to do is configure PC4 with the correct default gateway that matches the interface address on the router, the link local address, FE80::3. So it says implement the solution. So we go back to PC4, exit out of this, go to IP configuration, and just change the 2 to a 3 for the default gateway. And at this point, we could also check and see, is PC4 able to ping its default gateway now? Remember, IP6 isn't case sensitive, so lowercase FE80 will work fine. So now we're getting a reply from the default gateway, which is a really good sign. So if we go back to PC2 now and try to ping PC4, yes, it is working. And our traceroute is now getting us all the way there. It had gotten us almost there, but now it is successfully getting past subnet 4. And then over on PC4 in turn, of course, we send our echo request over to PC2, and PC2 is sending the echo reply back, getting a round trip time. So we've got 100% success. And if we do a traceroute, we are fully getting our 4 hops. Remember, each hop would be a layer 3 device. So we go back to our document and we say, is the problem resolved? And the answer is yes. And then you just want to go back to your table and then correct your addressing table as well, so that everything is correct.